If we track and optimize biomarkers of organ and systemic health, can aging be slowed? If so, what should we track? So here we can see biomarkers representative of many different organ systems. And more specifically, many of these biomarkers are included in the blood-based biological age clocks, PhenoAge and or aging.ai. And they include biomarkers of immune function, liver function, metabolic function, glucose, lipid panel, etc., and kidney function. But other biomarkers are not included, including biomarkers of muscle, bone, and body composition, or related to muscle, bone, and body composition, lung function, brain function and or health, and cardiovascular metrics. So with that in mind, the focus of this video will be what's optimal for the cardiovascular fitness metrics, including resting heart rate and heart rate variability. So let's start off with the resting heart rate, RHR, and seeing how it changes during aging. So this is Whoop data. Whoop is what I wear. I'm not sponsored by them. I've worn them since 2018. There are many different devices that can provide this information. So here we're looking at the average resting heart rate over the 20 to 50 age range. And this is data for women in red and men in blue. And we can see that resting heart rate increases for both men and women up to 50 years of age. What about older than 50 years? So for that, we've got to go to Fitbit data. And here again, we're looking at the average resting heart rate, but now we can see that the age range is wider from 20 to 85 years old. And in agreement with the Whoop data, we can see that resting heart rate does indeed increase up until around 50 years of age for women in green and men in blue. But after that, resting heart rate declines during aging from about 50 to 85 years old. So we can see that resting heart rate increases, then it decreases during aging. Now note that relatively low resting heart rates are found both in youth and in older age. So is a relatively low resting heart rate indicative of youth or aging? How can we answer that question? So for that, heart rate variability, HRV, provides more context. So what is the HRV? So the definition of it is, it's the variability for the time in between heartbeats. So for example, for a heart rate of 60 beats per minute, the assumption is that the heart beats exactly once per second, but that's not necessarily true. So here we're looking at 3 consecutive heartbeats, and we can see that the time in between those heartbeats is not exactly the same. 859 milliseconds, 793, and 726 milliseconds for those three, the intervals for those 3 intervals for each heartbeat there. So the time in between heartbeats is the variability that's calculated as heart rate variability. And more specifically, Whoop provides the RMSSD, that's the root mean squared of successive differences. So that's the data that I'm going to present as it directly applies to what I'm wearing or the data that I'm getting from Whoop. So let's have a look at how heart rate variability changes during aging. And we can see that here. Again, this is the RMSSD. This is the version of heart rate variability provided by Whoop. And note that all heart rate variability measurements are not the same. So it's an important distinction to know if it's the RMSSD or other heart rate variability measures. And this data is from the 20 to 60 year age range. And this is a study of more than 8.2 million people. So this isn't Whoop data. And note that we've got 2 different curves here. We've got the solid lines and the dashed lines with the data for women in red, men in blue. And note that the data, the solid lines, is heart rate variability data obtained early in the morning at 6 in the morning, and the dashed lines is at 6 o'clock at night. So we can see that heart rate variability is higher in the morning when compared with nighttime measurements. Now for me, Whoop provides the data in the morning, so while I'm asleep during the last sleep cycle. So that's the data that I'm going to focus on going forward. So with that, we can see that heart rate variability declines during aging, as shown there, with values of about 75, median values of about 75 in 20-year-olds, and values of about half of that, around 35 to 40, in 60-year-olds. So what about older than 60, going beyond this age range? So there are very few studies that have looked into this in older adults, at least very large studies that have looked at this. Here's one of them that's highlighted. And when looking at from youth up until 79 years old, we can see that heart rate variability does indeed decline during aging, starting from values of 53 milliseconds down to 19 milliseconds. But then something interesting happens, at least in this study, for the 20, 80 to 99-year-olds. And we can see that the heart rate variability is higher than expected based on the age-related decline with an RMSSD of 30 milliseconds. I mean, this would be something you'd expect to see for someone in their late 30s. So having this suggests that a higher heart rate variability than expected based on chronological age may be a marker of longevity. And in support of that, let's take a look at data for older than 99 years old, so data in centenarians. So again, this is the RMSSD, so heart rate variability, And the centenarians in the study, again, it's a small study, so we can't make definitive conclusions. We'd need to see more data. But for the 17 centenarians in the study that had an average age of 102 years, they had a median heart rate variability of 36 milliseconds. Now, that was significantly higher than the 84-year-olds that had a median heart rate variability of 24 milliseconds. But note that the centenarians didn't have higher heart rate variabilities than very young adults, 21-year-olds, that had a heart rate variability of about 58 milliseconds. So from that, we can see from these two studies that suggest that having a higher heart rate variability than expected based on chronological age may be a marker of longevity, but we'll need to see more studies to see if that will be true or not. So to address our question earlier, is a relatively low resting heart rate indicative of youth or aging? We can now answer that question. So at younger ages, we see relatively lower resting heart rates, but relatively higher heart rate variabilities. And conversely, at older ages, going even beyond 60 years old, we can expect to see lower resting heart rates, but also relatively low heart rate variability. Now, I've tracked both of these metrics since August of 2018, and I now have more than 1,500 days of data. So let's take a look at that data. Now, based on the population-based averages that I've presented on this slide, we'd expect to see an increasing resting heart rate and a declining heart rate variability over that 4-year period. So let's see if that's true. So let's start off with data for resting heart rate, and this is individual days. So this is 1,500, more than 1,500 days of data. Each dot is a single day of data. So when I first started tracking in 2018, my resting heart rate was about 51 beats per minute, which was then reduced, and this is the year average, was then reduced in 2019 to about 49 beats per minute, further reduced in 2020 to 48.1, further reduced in 2020, further reduced in 2021 to around 47 beats per minute, and my current average in 2022 is 44.9 beats per minute. Now, besides just looking at averages, year-to-year averages, we can calculate whether year-to-year changes may be significantly different using a two-sample t-test. So when doing that, we can see that each of these years, 2019, 2020, etc., when compared to 2018, are significantly lower based on the p-value, with a p-value less than 0.05 being statistically significant. And then we can also compare year-over-year changes, not just 2019 versus 2018. So when doing that, each of the years from 2020 to 2022 is significantly better than the preceding year. So a significantly reduced year-over-year, YOY, resting heart rate since 2018. So from that, we can see that I've consistently reduced my resting heart rate over the past 4 years. So is that good or bad? And the reason that I asked that question is because we know that a relatively low resting heart rate can be found in youth, but also in advanced age, as shown there. So note that I've resisted, at the very least, I've resisted the age-related increase for resting heart rate. Based on this data, we'd expect to see an increasing resting heart rate over the last 4 years, but that's not the case. I've actually reversed that. So to address that question, is this good or bad, the consistently declining resting heart rate? For more context, let's have a look at heart rate variability data since 2018. And that's what we can see here. So when I first started tracking in 2018, my average heart rate variability was around 47. In 2019, I increased it to 56. And using a two-sample t-test, that was a significant increase. So I significantly improved heart rate variability 2019 versus 2018. In 2020, 57.8 milliseconds for an average for the year. And then when compared with 2018, still significantly higher, but just outside of statistical significance for being a year-over-year improvement. So from that, we can conclude that 2019 data was not different from 2020 for heart rate variability, although it was better than when I started in 2018. But then in 2021, I regressed. You can see my average heart rate variability was 51.9 milliseconds for the full year daily average. And this is better than 2018, but significantly worse than 2020, as shown there. So a major goal of 2022 was to get my heart rate variability back up. And we can see that thus far in 2022, my average heart rate variability is 59.4 milliseconds, which is better than when I started in 2018 based on a two-sample t-test, and better year over year when compared with 2021. So from that, we can see that I've increased my heart rate variability over the past 4 years with that hiccup in 2021. Now, let's put these data into context. How do these data compare with age-related changes for heart rate variability? So we can the expected median heart rate variability based on my chronological age, which I'll be 50 in January, would be 35.1 milliseconds based on how it changes during aging. Now, to put my 2022 data into context, at worst, 59 milliseconds is just above the high end of the heart rate variability range for my chronological age. But at best, this is the median heart rate variability that will be found for someone that's about 22 years younger. So whether the truth is just good for my chronological age or a value that you would expect to see in someone much younger, the truth is probably somewhere in the middle. All right, so now we can address that question again. Is a relatively low resting heart rate indicative of youth or aging? So in my case, having a relatively high heart rate variability plus a low resting heart rate, more specifically 59 for heart rate variability, 45 for resting heart rate in 2022, that suggests cardiovascular youth. In contrast, for my chronological age, a lower heart rate variability, but a higher resting heart rate. More specifically, expected data would be 35 for HRV, 57 based on chronological age. So we can see that 59.45 is better than 35.57. Higher heart rate variability, lower resting heart rate suggestive of CV youth, cardiovascular youth. All right, so what's contributing to these improvements for resting heart rate and heart rate variability? How am I doing it? So a big factor may involve body weight. So this is my average monthly body weight from August of 2018 through September of 2022. So over the same period that I've been tracking these cardiovascular fitness metrics. And we can see that, before jumping into the data, note that I record my body weight every morning after, pee and poop and fasted. So when I first started, we can see I was heavier than where I am now. So around 159 pounds, where currently now I'm about 151, 152. So what's the relationship for body weight with resting heart rate? So here we're looking at my average monthly resting heart rate over that same time period. And the two curves look interestingly similar, where they could even potentially overlap. And more specifically, when we look at the periods where my body weight was reduced over time, we can see that resting heart rate also declined over that same time period. Conversely, when my body weight went up for given periods of time, resting heart rate increased. So that then raises the question, is body weight significantly correlated with resting heart rate? So for that, let's look at individual data points for daily resting heart rate versus body weight in order to calculate the correlation between the two. And we can see that that correlation is positive, meaning as body weight increases, resting heart rate increases too. Or as body weight increases, that's significantly correlated based on that p-value there with a higher resting heart rate. Conversely, as body weight approaches 150 pounds, that's significantly correlated with resting heart rate approaching 45 beats per minute. And because my most recent body weights or average monthly body weights are approaching 150, that shouldn't be a surprise then why my resting heart rate is around 45 beats per minute. All right, so what about heart rate variability? What's the relationship for body weight with heart rate variability? So this plot for average monthly heart rate variability as shown there isn't as clear cut as the data for resting heart rate, where you can't overlap it with the body weight trace, but we do see some apparent trends. So as body weight has declined, as shown there by the green arrows, we can see increases for heart rate variability. And conversely, as body weight has increased, we can also see that my heart rate variability has decreased during those periods. Now, it's not as clear cut though. So what about the correlation? Are they significantly correlated? So we can see that data here, daily heart rate variability versus body weight over the past 4+ years. And again, we see a significant negative correlation, which means that as body weight increases, that's significantly correlated with reduced heart rate variability. And conversely, as body weight approaches 150 pounds, we can see that my heart rate variability approaches 60 milliseconds, which is pretty close to where I am currently for 2022. So to answer the question, what's the relationship for body weight with heart rate variability and resting heart rate? At least for me, it may be different for others. Resting heart rate and heart rate variability approach youthful values as body weight decreases. Now, note that this may not be the only factor that's impacting my data. Daily physical activity also, and I should mention obviously, impacts cardiovascular fitness metrics. So let's take a look at that data. So as a measure of daily physical activity, I track the average daily heart rate, which is provided by my fitness tracker. So I mentioned I use that as an index, the ADHR, as an index of daily physical activity. And why that's important is because if you walk 1,000 steps on flat ground, that'll result in a lower heart rate when compared with walking 1,000 steps up a hill. So when compared with tracking steps, tracking heart rate may be a more informative measure of the effort involved in your steps, or the overall effort involved in your daily physical activity. But note that a higher average daily heart rate isn't just indicative of physical activity. I've had days where I wasn't very physically active, but had some, emotional stress going on. And fortunately, those days are rare. But I've seen heart rates on those days that can even surpass my days that include workouts. So obviously, I try to minimize as much non-workout stress as possible to limit that variable. All right, so what's the correlation for the average daily heart rate with next day resting heart rate? And we can see that here. So this is data from March of 2020 through September of 2022. So I have far less data, only about 900 days. Unfortunately, I didn't have the idea to track the average daily heart rate until about 900 days ago, but I wish I had tracked it earlier so I'd have a lot more data. Nonetheless, we can see that there's a significant positive correlation between how active that I was and my next day resting heart rate. So that suggests that too much daily activity and too often will be bad for the resting heart rate. All right, so what about heart rate variability? How does physical activity affect next day heart rate variability? So we can see that here, and we can see that, again, a significant negative correlation, which suggests that the higher my average daily heart rate, the lower my next day heart rate variability, which again, too, suggests too much daily activity and too often would be bad for heart rate variability. So with that in mind, finding the balance between active and rest days will be important for optimizing resting heart rate and heart rate variability. Now, I can't say how that would work for others. I think that's an individual thing. You'd have to determine, after a workout day, how many days you may need to recover based on tracking heart rate variability, resting heart rate, and the average daily heart rate. But to illustrate in my data what that looks like, so we can see that on my active days that include a workout, my usual workout, my average daily heart rate is 59 beats per minute. So starting from the middle with that 59, we can then see over the next 3 days, I purposely titrated activity downward so that it was lower than 59 beats per minute, allowing my cardiovascular system to recover and potentially enabling maximal improvements for resting heart rate and heart rate variability. And then you can see by the 59 spike at the end, then I had another workout. So that's a 4-day cycle, workout and then 3 relatively lower intensity days and then workout again. But I also have a 3-day cycle. As you can see on the left side of the graph, there was a 59 and that was a workout day too. And then I titrated activity downward over the next 2 days. After then I had another workout on day 3. So 3-day cycle for exercise followed by a 4-day cycle in this representative image. And that's basically the approach that I've stuck to for the last few weeks. I try to stick to a 3-day cycle, but sometimes, work-life balance gets in the way. All right, that's all for now. If you're interested in more about my attempts to biohack aging, check us out on Patreon. Before you go, we've got some discount links that you may be interested in. If you want a blood test at home, you can do that using the company Quantify. So discount links for all these will be in the video's description. If you want to measure your epigenetic age using Horvath, Hannum, or Dunedin Pace, we've got a discount link for that. Oral microbiome composition, and I should have that update video coming within the next few weeks, so stay tuned for that. If you want to track your own, there'll be a discount link for that. If you want to track your diet using Chronometer, discount link for that. Or if you'd like to support the channel, you can do that with the website, Buy Me a Coffee. And again, all of these links will be in the video's description. Thanks for watching. I hope that you enjoyed the video. Have a great day.